Hey everyone, this video is about variance and standard deviation. In the last video, we talked about how anytime you have a measure of central tendency, where you say, I think this is going to be what the next number will be, you need to have some measure of variability, which is how far off do you think you'll be. So anytime you use the mean or the median to predict what is expected, you have to include a measure of basically how far off do you think you'll be. And that's where variance and standard deviation come in. So variance and standard deviation are they're really just very closely tied together ideas. It's not like you have to learn two completely different ideas here. It's one idea. As you'll see. Basically, what it does is it starts with the idea of a deviation. Deviation in statistics is how far is an individual from the mean. And this is the mean, not the median or mode. It has to be the mean. But a deviation is really just written as X being an individual score. It could be like an individual student in class minus the mean. That would be the mean of the students in the class or something like that. So it's a way of saying, well, sure, everybody has like a mean. How far apart is each individual from the mean? So with that in mind, a deviation, that's a pretty important score. We have a measure called variance. And the reason for that will come to be a little bit more clear later on, I think. The variance is like, on average, how far are people from the mean squared? And the reason why we add that squared part is puzzling probably at first, but it makes a lot of sense once you see what happens when we look at deviations. In addition to variance, we have the standard deviation. So that's on average, so the standard deviation is on average, how far is a person from the mean? Well, the standard deviation is actually the square root of variance. It is like, okay, variance tells us on average how far is a squared individual's deviation. Standard deviation just unsquares that. I can't think of the word for that now. Unsquare. So the standard deviation unsquares the variance. There we go. All right, so it turns out to be a very useful number, as this graph shows. This is one of those graphs that shows a very perfect normal curve as printed from a calculation from a mathematical formula. When we actually collect data from samples, it doesn't look this perfect. But anyway, so this is a perfectly normal curve, with this right here being the average score. And notice this zero here, we'll get to that in about 3 or 4 classes. That zero means that it's 0 standard deviations from the mean. But 1 standard deviation from the mean says that on average people are this far from the mean. And on average people are this far from the mean. These are the same number here. We don't have one number to say how far people are above the mean and another below the mean, because it's something that we apply to normal distributions where it is more or less symmetrical. All right, so variance and standard deviation. I'm going to take like an approach here where I show you 2 different things, but ultimately what I want you to do is think about this as like an average. Variance and standard deviation are both averages. And if you remember what an average is, average means you just add everything up and then you divide by the number. So if there are 10 people in a sample, you add up all of their scores, you divide by 10. And that's kind of what variance and standard deviation does, except instead of doing that with the basic scores, it's doing that with variability. But let me see here. So for variance and standard deviation, what we do is we sum up not the individual scores, which we would do for normal average, but we sum up squared deviations. And you'll see in the slide or two here why we use squared deviations. But as we do this, as we get this numerator, when we sum everything up and we work with squared deviations, this number here, the sum that we use to calculate our averages, is called the sum of squares. And that's because we are summing up squared deviations. I'll show you a table here in a minute that I think explains that fairly well. But before we do this, you should know there are two different ways that we calculate sums of squares. There's one of them that's used to show what it means, and I think it does a really good job of showing what it means. But when you're actually doing the work, there's another approach called a computational approach, which I think is a little bit easier. So we'll start with what I would say is the way that does a good job of demonstrating what sums of squares is. And I'd call it the tabular format because we put it in a table, and this table has 4 columns. And what this will do is allow us to start calculating the sum of squares. So the first thing I want you to notice, though, is that this is a group of sensation-seeking scores. So in the classroom, we actually had people fill out sensation-seeking scales. That's like the extent to which you like thrill-seeking activities. And I got a group of numbers, and you can see here it's a pretty tight-knit group of numbers. So that's what we're dealing with. We're starting with a set of raw scores. Now, the next thing we're going to do is we're going to calculate the mean. So M here means the mean of those scores. So down here, in order to calculate the mean, I know that I have to add up every individual. So 4 plus 6 plus 9 plus 5 is 24. And then to get to the mean, I'll divide that by 4, because there are 4 individuals in my sample. And when I look at that, what I wind up with is 6. So a way to think about this is that, well, we have individuals at 4, 6, 9, and 5 on the scale, but the mean would tell us that, gosh, they should be getting 6s all the time. So this number here, the 6s, it's actually incorrect 3 of the 4 times. Is that a problem? Well, I don't know. But look, if you look at this, the next one here is called a deviation. The deviation is the individual's score. So this is an individual student in our class, and that is the average score of our class. So deviation basically is saying that this individual got a 4, but we'd expect a 6. That's what a deviation does. So if I fill in this column right here, what I see is my deviations go -2, 0, someone's exactly what we expected them to be, +3, someone scored 3 points higher than what we'd expect them to, and -1. So notice that in this column here, we're talking about how far people are from the mean. Not just how far they are, but that negative or positive sign says if they are higher or lower. Now, what I'd like to do in stats is say, well, here's what people's scores are, and on average, they have a 6. However, I know that just because there's an average of 6, not every individual has a 6. And that's what this tells us. So I'd like to be able to summarize this or average this in the same way that I averaged the original scores. On average, there's a 6. And then on average, people are blank number from 6. Now, I can't just average this and say on average how far are people from the mean, because if you notice what happens here, if we add this up, that's 0. So I can't add that up and divide by 4. In fact, the reason that we have the sum of squares is because this will always be 0. And so we have to have some way of creating a column of positive numbers. You could just do absolute value, create a positive number by creating absolute value. But it turns out, for reasons that has to do with calculus, it's easier to square these. All right, so over here, the last column in the table, x minus m, that's the deviation. The deviation squared is what we need in order to get our final calculation. So, if I square each of those, notice I got -2 is now 4, +3 is 9, -1 is 1. Now that they're all positive, they're going to add up to something other than 0. And that number is 14. Whoops, sorry. All right, so the sum of squares number here is 14. That means that the total squared variability, total squared deviation, is 14. Now, what do we do with that? That's actually just an intermediate step. We actually use that number to calculate what we call variance and standard deviation. So these are measures of variance. Here we have variance, and this is written as sigma. That's the Greek S, sigma squared is the sums of squares divided by n. Now what that means is that I'm going to go back to that last table and get the number 14, where we calculated sums of squares, and then divided by the number in the sample. And then I'm going to say the variance is 3.15. Now that's the average squared distance from the mean. Now, I would like to point out that this is from a population. One of the things that happens in stats is we don't ever actually work with populations. We usually work with samples. So you're going to find out there's an adjustment that we make that fits a sample. Okay. But for population, that's what we had been dealing with. That's what we would come up with. Now, the standard deviation is really just the variance, sigma squared. It's really just that, take the square root of that. So if the variance, the squared value up here is 3.5, we just want to take the square root of that 3.5. Come with 1.87. All right, so over here in the sample size, just to make it clear what I'm talking about here, the population means that you've actually measured every single person in the entire population. That's pretty rare. We're much more likely to use the sample. So in the sample, instead of the Greek, we have letters, so like SD squared. And instead of sums of squares over n, we have sums of squares over n minus 1. So still an average. This average, we'll see later, this is called degrees of freedom. We'll see that later. But the average here, what that does, it says, okay, we're going to admit that we're just estimating things here. We don't know what's actually true. We do know that if you take a sample, that you're probably going to underestimate the variance. You're going to underestimate the population. And that's why we have that value right there. So as you look at this table, what you'll see is that for variance, what we do is just take n minus 1 instead of n, otherwise same concept. And in the sample for standard deviation, we do n minus 1 instead of n. So again, it's the same concept, but what we're doing is using that n minus 1, we are able to sort of adjust our estimates of what a standard deviation or variance is for a population. All right, now I told you earlier, I was going to show you the long way to do that because it is a way of showing what everything means. That's what we did right here. This is the tabular format. We use a table to calculate all this. What I would encourage you to do as you're preparing for projects and tests and things like that is to use a shortcut version of that. So if you just take a break and look at this right here, this is a formula that allows you to get the exact same answer that you get from that prior screen, except in this case it goes a lot faster. So sums of squares, SS, is equal to the sum of the squared x's minus the sum of the x's squared divided by n. So here's how that works. If you want to use this method to calculate sums of squares, you add up the x's, which is 24. Over here I've squared each x value. So 4 is 16, 6 is 36, 9 is 81, and so on. And then I've added them up. So the sum of the squared x's is 158. Now, if you put that into the formula, 158 minus 24 squared over 4, you get 14. And of course, 14, as we saw earlier, using the slow method, is our sum of squares. So I can plug that into an equation to calculate the variance or the standard deviation.